Okay, let's start the theorem and let's start this lecture now. So Bessel's inequality we have done. So now let us start with the following theorem. If let X be an inner product space, let X be an inner product space IPS, okay, and this set U1 U2 be orthonormal set, be a countable orthonormal set in X, be a countable orthonormal set, the countable orthonormal set in X. And K1 K2 they are scalars, and K1 K2 so on and so forth are scalars, they are belongs to K, belongs to K. First part is if this series is convergent, series K and UN converges to some point X, converges to some X in X2, some X in X, sorry, not X in X, yeah, okay. X is in a product space here, it's okay, it's X not H. X in X. Then X UN, then this what are these scalars? Kn is they are equal to X UN, okay, X UN is equal to Kn, means these scalars can be determined by the point X and these UNs orthonormal set for each n, for each n, for each n greater or equal to 1, and one more thing, that the series is convergent. This is in L2 series mod of Kn square, this series, and runs from 1 to infinity. This thing is finite. But the first part, if the series, this series Kn UN converges to some point X in X, then these scalars Kn they are given by the inner product X UN, and the series of the scalar they must converge square summable, okay. And conversely, and the converse also true, if this series is convergent, it's square summable, then the series X U K and UN it will converge in X. That's the converse part. That's called the Rees-Fischer theorem. That is second part. It's Rees-Fischer theorem. Okay, so what's this? If X is an inner product space, so that's already given. X is inner product space, so we don't need to mention it again here.
That's sure आ रहा है बैकग्राउंड.
Sure. So ये लैपटॉप का शायद शोर आ रहा है. Okay, not do anything with this. Okay. This is second part is the Rees-Fischer theorem. Okay.
Yes.
So in this, it's actually the converse of part A. So it states that if this series K and square, okay, this series is convergent and runs from 1 to infinity, it's finite thing, okay, this is finite and this is finite, then the series K and UN, this converges in this series and runs from 1 to infinity, it will converge in X. इज कन्वर्जेस इन x। तो ये इसका उसका कन्वर्स है, फिर ए पार्ट का कन्वर्जेस इन x। प्रूफ। So let's prove first part. First part is very simple. First we see that these kns, they are equal to x u1. Okay, kn is equal to x u1. So proof of a part. So assume that this a part, assume that this series kn un, it will converge to x in x. So assume that x is equal to sum kn un and runs from 1 to infinity. Okay, so we calculate x un. Okay, we will show that x inner product x un is equal to kn. We have inner product x un. What's x? X is the series. So let me write like this: j runs from 1 to infinity, kj uj, then un. Okay, so this is equal to since the inner product is continuous in both the variables, so it's equal to summation j runs from 1 to infinity, it will be here kj times uj un. Reason, because by linearity and continuity in the first variable and continuity of inner product. Okay, continuity of inner product in first variable, that's the reason. Okay, so now if you expand this sum, so for j equal to n, it will be un that's equal to 1. So that's at the nth term will be kn inner product un that's equal to kn. और बाकी जो भी टर्म्स है, since this set is orthonormal set, so that means uj un inner product uj un is equal to 0 for all j except j equal to n, and for j equal to n it's equal to 1. So this is just equal to kn. Okay, because inner product uj un is 0 for all j greater or equal to 1 except for which value? Except for j equal to n, and for this value, what's the inner product un, it's equal to 1, right? So therefore our kn is equal to inner product x un. ये आपने चेक किया है। Now you want to calculate this series of kn as a square with square power. Now let's find that. So that actually follows by Bessel's inequality, inequality part. And now let's find this sum. Now let's find this sum. It's very simple. Let's find this sum, summation mod kn square and runs from 1 to infinity. What's this kn? This we have proved it's equal to summation, sorry, it's n runs from 1 to infinity, n runs from 1 to infinity. Okay, sum n runs from 1 to infinity mod of inner product x with un whole square. Okay, but we know that whenever x is equal to series here we have x is equal to now let's see, this is equal to norm x square. This is equal to norm x square because what? Why? Because x is equal to summation n runs from 1 to infinity kn. What's the value of kn? Kn is the inner product x un and un. तो आप Bessel's inequality देख सकते हो. By Bessel's inequality, equality holds in the Bessel's inequality if and only if x is equal to this, and here x is equal to this, because x is the series kn un, where this kn is equal to inner product x un. So because this and by Bessel's inequality, and by Bessel's inequality. So here equality holds, okay. It's equal, and this norm x squared is always the finite thing. So that means summation n runs from 1 to infinity mod of k n square is the finite thing. This is so that's the first part. Now the second part, which is the Fischer theorem. Second part, second one. That's the Fischer theorem. Okay, so we have to assume that this series mod kn square n runs from 1 to infinity is finite. Okay, suppose this is finite. Now what we do, we define we try to construct a Cauchy sequence. So in the second part, x is Hilbert. Okay, so I forget to mention that it's Hilbert space. Okay, in the second part, x is Hilbert space. Okay, so if this thing is and x is Hilbert, okay, and x is Hilbert space, you should mention it here. X is hs means Hilbert space, then this holds, then this series converges in x. So if the series is finite and x is Hilbert space, so second part को फिर से लिखिए. So in the second part, the inner product space is Hilbert, so it's complete. Okay, it's a complete normal linear space. So assume this, and x is Hilbert, Hilbert space. Now what we do, we construct a Cauchy sequence. Okay, from this we construct a Cauchy sequence, and then we apply this x is Hilbert, so every Cauchy is convergent, and finally we see that the limit is that series actually. So let's try to find construct this. Let's try to construct the Cauchy sequence. So how do we do that? For each m, we define, for each m 1 to infinity, we define xm. What's xm? That's the sum of the m terms. Okay, its summation n runs from 1 to m k n u. Obviously this thing is in h. Okay, it's in h, because un is in h, u1 is in h, u2 is in h, everything is in h, and it's a finite linear combination of elements of h. So this thing is in h. So xm is in h for each m, for each we show that this xm is the Cauchy sequence. Okay, so let epsilon be any positive number. This is a positive number. Now this thing is finite. It's a finite thing since series n runs from 1 to infinity mod of kn square is finite. So what we can have, we deduce that there exists some capital N such that this summation n runs from, say, capital N to infinity mod of kn square so let's write it less than, say, epsilon by 2. Okay, or you can write n plus 1. Okay, that only matters, n plus 1 infinity, it's less than epsilon by 2. Okay, we have norm for m minus j, for for m greater than j, for m greater than j, we have norm of xm minus xj square. Let's calculate this difference where m is greater than j. Okay, so you can see this is this xm, it is the sum of the terms, sum of m terms. Xj is the sum of j terms. Here is the definition of xm. Okay, so xm means sum of the m terms, xj means sum of the j terms. So you are subtracting j terms from m terms, because here m is greater than j, so there remain how many terms? M minus j. So let's write it like this. It's equal to what is this? This is summation n runs from 1 to m. Okay, this it's then k n u n minus summation n runs from 1 to j. This is a k n u n whole square. So this is equal to norm. This is equal to summation n runs from 1 to j. This is k n u n plus summation n runs from j plus 1 to m. Okay, मैंने पहले सम को मैंने ब्रेक किया, पहले j टर्म्स मैंने अलग ली, उसके बाद जो m j प्लस 1 से लेकर m टर्म्स इनको मैंने अलग से सम किया है. Okay, minus its summation n runs from 1 to j k n u n whole square. These two will go. This is equal to norm summation n runs from j plus 1 to m k n u n. Okay. Okay, and this you can verify that this is equal to. Now since this un, it is an orthogonal set, so it's square here. So norm of square of norm of sums is equal to sum of squares of normals actually. So this is equal to, and we know this. So this is equal to summation by Pythagoras theorem. You can apply here Pythagoras theorem. M. This is a norm of k n u n square. You can see it. This is very simple. But norm un is 1 because the set is orthonormal, and this k n is scalar, so it is mod of k n times norm of un. So this is equal to summation n runs from j plus 1 to m mod of k n square. Okay, k n square. So this is norm xm minus xg.
सर अगर अब j m के बराबर होगा उस टाइम कैसे हम ब्रेक करेंगे?
उस टाइम ये 0 के बराबर होगा. उस टाइम ये जो डिफरेंस होगी इट विल बी 0 अगर j m के बराबर. ठीक है, ये डिफरेंस 0 के बराबर आ जाएगी उस टाइम. तो अगर m ग्रेटर देन j होगा उस टाइम आपके पास ये टर्म्स रहेगी इसमें, these terms. So this is xm minus xg. Okay, so we have seen that here, if you want to check that again, this thing for each epsilon positive, we have this. Okay, this one, let's apply this here. How do we apply this? This is summation n plus 1 to infinity actually. So this thing is less than epsilon by 2. So I want to apply it here now. uh, so norm of xm, so let's see this. So this is a norm of so now it means that norm of xm minus x capital N is also so this gives let's choose we can choose this actually, because we know that for each epsilon first I can find capital M such that such that sum of the terms of mod of x and k and square is less than epsilon by 2 for n runners from n plus 1 to infinity. I can choose this n sufficiently large. I can choose so yeah, or I can choose m large so that m is greater than n plus m is greater than n. Okay, so choose let's choose m greater than m. Okay, let's choose m greater than m. So let's write this here. This is sorry, in the previous way we have this thing. तो हमें यहाँ पर फाइनली हमें क्या आया था यहाँ पर, सो इट वाज इक्वल टू समेशन summation n runs from so it was j plus 1 to m. Okay, this thing ये हमें मिला था. Okay, so this was actually norm of xm minus xj whole square where this m is greater than j. Okay, so choose this m greater than capital N, then we have norm of xm minus x capital N its square, it's equal to summation n runs from capital N plus 1 to m mod of k n square. Okay, so this is obviously less than summation n runs from capital N plus 1 to infinity mod of k n square, and this is less than epsilon by 2. Okay. So finally for m n greater than capital N, we'll find this thing, norm of xm minus xn square. Okay, xm minus xn. Okay, this is xm minus xn square. This should be now xm minus xn square, then xn minus x xm minus xn plus xn minus xn. Okay, both are less than epsilon by 2. So so let's do first this thing. So let's write choose m. This implies यहाँ पर आप ये लिखिए, this implies. So I think you should write here here you should write here epsilon square divided by 4. Okay, so epsilon square divided by 4. So why I am choosing epsilon square divided by 4? So let's look at here. This is less than epsilon square by 4. So this gives without squaring. So let's apply square root on both sides. xn minus xm will be less than epsilon by 2. इसका नाम आप 1 रख दीजिए. दिस थिंग. आपको ये बात समझ आ गई मैंने क्या किया? मैंने ये जो है ना यहाँ पर मैंने एप्सिलॉन बाई 2 की जगह पर एप्सिलॉन स्क्वायर बाई 4, बिकॉज इट्स ट्रू फॉर एनी एप्सिलॉन फॉल्स ट्रू फॉर ईच एप्सिलॉन आई कैन फाइंड कैपिटल N with this property because of the convergence. So instead of epsilon I will write here epsilon square over 4. So then here in the next page in the next page, you will see this norm xm minus x capital N whole square, it is less than epsilon square by 4. So let's apply the square root on both sides. You will find norm of xm minus x capital N less than epsilon by 2. So now we don't need square here, okay? So actually I want to apply triangle inequality, that's why I'm doing this. This is equal to a norm of xm minus x capital N plus x capital N, okay, minus xn. Let's apply triangle inequality. It's less or equal to norm of x capital M minus xm minus x capital N plus norm of xn minus x capital N. And both the things are less than, because for whenever m is greater than n, this norm xm minus x capital N is less than epsilon by 2. So here both m and n, they are greater than n. So norm xm minus x capital N is less than epsilon by 2 plus norm xn minus x capital N, it's also less than epsilon by 2. So that's equal to epsilon. So that means for each epsilon positive, I can find capital N such that whenever mn greater than n, xm minus xm, norm of xm minus xn is less than epsilon. So which means that the sequence xn is a Cauchy sequence. So therefore this sequence xm, m runs from 1 to infinity, is a Cauchy sequence, is a Cauchy sequence in x, and x is Hilbert space, so hence it converges, and hence it converges in x, okay, it converges in x. वही तो हमें प्रूव करना था बी पार्ट, इट कन्वर्जेस इन एक्स. सो दैट इज दिस सीरीज n runs from 1 to infinity, kn un converges in x. Why this series? Because xm is actually this, it is a sequence of partial sums. Actually xn is actually this, n runs from 1 to m. So this will converge. So that means this converges in x. So this is the second part. Now let's do the following theorem, which is very important. So first we define the maximal orthonormal set, okay? Maximal. So it's called orthonormal basis actually, orthonormal basis. Orthonormal basis. Orthonormal basis. So एक तो आपने बेसिस की है ना, शेडर बेसिस, जो आपने वो की है वेक्टर स्पेस में डिफाइन बेसिस, हैमल बेसिस जिनको हम कहते हैं. हैमल बेसिस एंड ऑर्थो, दे आर टोटली डिफरेंट थिंग्स. So orthonormal basis में actually it's related with the convergence actually. So we can't define orthonormal basis in vector space, okay? Hamel basis is different in both vector space as well as in normal linear space. So but the concept of orthonormal basis, it is in the Hilbert space, it is in the inner product space actually, okay? Inner product space. So here we must need convergence. So but for Hamel basis we don't need any type of convergence. This is a totally algebraic concept, okay? Hamel basis. So what's this orthonormal basis? So it's actually a maximal orthonormal set. So let's define this. An orthonormal set जैसे हैमल बेस है ना, इधर दे में बी काउंटेबल, दे में बी फाइनाइट और इनफाइनाइट. सो इस तरह से ऑर्थोनॉर्मल बेसिस का भी वही है. इट में बी काउंटेबल, इट में बी इनफाइनाइट, इट में बी काउंटेबल, इनफाइनाइट, uncountable, okay? It may be uncountable also. So an orthonormal set which is indexed by this u alpha, okay, alphas. So this is the set. It may be अगर finite set होगा, it will be u1 u2 up to un, okay? in that case. So if it's countably infinite, then it will be u1, u2, so on and so forth. If it is uncountable, then you will write it like this, u alpha. Okay. An orthonormal set in a Hilbert space. In a Hilbert space. In a Hilbert space. In a Hilbert space X. Okay. Okay, let's we denote Hilbert's, usually denote Hilbert space by H. In a Hilbert space H. In a Hilbert space H is said to be an orthonormal basis. Is said to be an orthonormal basis if for any, अगर कोई भी ऑर्थोनॉर्मल सेट आपके पास होगा, if for any orthonormal set E of H, this set U alpha is contained in E. अगर कोई और ऑर्थोनॉर्मल सेट होगा जो इस ऑर्थोनॉर्मल सेट को कंटेन करे, then equality must hold. Then this U alpha must be equal to E. Means that there is no any orthonormal set which properly contains this one. तब जाके इसको हम कहेंगे ये orthonormal base. In other words, it's actually maximal. In other words, it's actually maximal. So that's a maximal. That's a maximal orthonormal set. That's a maximal orthonormal set is called a maximal orthonormal set is called an orthonormal basis. Is called an orthonormal basis. Okay. Is called an orthonormal basis. Maximal orthonormal set. Okay. Now we need to find the existence. Does it really exist, maximal orthonormal set? क्या ये एग्जिस्ट हो रहा है, वो हमें चेक करना है. जैसे हैमल बेसिस एग्जिस्ट हो रहे हैं, क्या ऑर्थोनॉर्मल बेसिस भी एग्जिस्ट हो रहे हैं, वो हम इसके बाद डिस्कस करेंगे. एग्जिस्टेंस ऑफ orthonormal basis. Okay, so let H be a Hilbert space and X not equal to 0 belongs to H. Then this set X over norm of X is an orthonormal set. Is an orthonormal set. So let's denote it by E. So let E be this set. Okay. So E is an orthonormal set. Now what we do, we define this set. This set. It's U alpha such that U alpha is an orthonormal set. Is an orthonormal set and E is subset of this set U alpha. E में तो एक ही element है. E is subset of this. Then what we do, we define a order on this. Now let's define the inclusion order. So with respect to the inclusion, it will be a partial order. Then the set this is a partially ordered set with respect to the inclusion order. Then then this is a partially ordered set. Partially ordered set with respect to the inclusion order. With respect to the inclusion order. Okay. With respect to inclusion order. Directly with respect to the inclusion. So that's we define. We say two elements are related if and only if one is continued in the other. So that is given. That's given two elements, say u alpha, u beta. In this we see this element is related to this element if and only if this set u alpha is contained in the set u beta. That's the order of here. So now if you take any chain, let this be a chain in this, then you can easily verify that these elements then clearly union of the members of C, union of C, where C belongs to this cursive C, is an orthonormal set, because each C is orthonormal set, and this is chain. It's in increasing or decreasing order. You can represent the elements of cursive C as an increasing or decreasing order because it's a chain. Any two elements are comparable, so you can find out this union of members of this chain. So each member of the chain is orthonormal set, and you see the union is also an orthonormal set. This union is an orthonormal set. Union is an orthonormal set containing the set E. Okay, so E set को contain E is a singleton set because each C contains the sets E. Each member of the cursive C contains this set, particular set E. So union also contains a particular set E. So you just verify this. It's a chain. Okay? It's an orthonormal set. So hence this is an orthonormal set, and hence an upper bound. Hence an upper bound. ये इसका upper bound होगा. Upper bound of this chain. Okay. So thus every chain has an upper bound. Thus every chain has an upper bound. Has an upper bound. So therefore by Zon's lemma, this set has a maximal element. Therefore by Zon's lemma, this E has a maximal element. Say u alpha. So u alpha इसका maximal element है, और यही जो maximal element है, it's a maximal orthonormal set, and this and hence every Hilbert space has a orthonormal basis. Orthonormal. This is just the existence of the orthonormal basis. Okay. Okay, so next lemma, which is very important. What about this set? अगर आपके पास say u alpha है, आपके पास set ये basis है, it's orthonormal basis. Okay, it may be countable or uncountable. If it is countable, then it's fine, then you can find the series of series x and un, okay, if it's countable set. So series is defined only for countable sets, okay, you must sum or countable set. So n runs from 1 to infinity like. So we don't have series over an uncountable set. Cannot define the series or uncountable set. So the problem is when this set is uncountable, how can you calculate this series? Can you calculate this series? And for this we have a lemma which is very important. What is this kn actually? Kn is the inner product of x un, okay, x un जो हमने अभी वो lemma किया है. If this converges in x, if this is in h, then this kn is like this. It's inner product of x with un. And we will prove a lemma which states that the set u alpha such that inner product of x with u alpha is not equal to 0. So this u alpha, it may be uncountable. There are uncountable many u alphas, but those u alphas where the inner product of x with u alpha is not equal to 0, this set is countable. This set is countable. Say this is say u1, u2, so on and so. Suppose it's countable infinite. So then the series, if you want to find all the series, if you want to define this k alpha equal to the inner product x with u alpha, so there are only countably many non-zero such scalars. So that means we can calculate this series x and un, and runs from 1 to infinity. So this is just a series with respect to given orthonormal basis. तो ये सीरीज आप कैलकुलेट कर सकती हो for a given x. For any given x, you can find countably many uns where the inner product of x with un is not equal to 0. So this determines actually this gives actually the whole series. You can say it's x alpha u alpha whole, for whether alpha is countable or uncountable. But it turns out that this is actually only countable, because we have only countably many k alphas which are non-zero. The rest are all equal to 0. तो वो जो जहाँ पर ये ज़ीरो है ना, तो उन के अल्फाज को हम नहीं लेंगे, जहाँ पर नॉन ज़ीरो है वही के अल्फाज हम लेंगे, और वो सिर्फ काउंटेबल है. दे आर ओनली काउंटेबली मैनी. सो दिस इज आवर लेमा एक्चुअली. सो लेट्स फर्स्ट स्टेट दिस लेमा. सो दिस लेमा इज वेरी इंपॉर्टेंट. तो अनकाउंटेबल सेट को आपने काउंटेबल सेट में वो सिर्फ काउंटेबली मनी यू अल्फाज के लिए वो जो स्केलर्स है वो नॉन ज़ीरो है. खुद वो सेट अनकाउंटेबल भी हो सकता है. जैसे आपके पास देखिए सेट ऑफ रियल नंबर इट्स अनकाउंटेबल. सेट ऑफ इंटीजर्स से नेचुरल नंबर इट्स काउंटेबल. अब देखिए अनकाउंटेबल कितना बड़ा सेट है, और काउंटेबल देखिए दीज आर द नंबर्स काउंटेबल. Cardinality, it is a cardinality of the countable set, countable infinite set is LF naught, and cardinality of the real number it's 2 per LF naught. That's the C. So अब आपके पास यू अल्फा देखिए. यू अल्फा, ये यू अल्फाज इतने हैं जितने आपके पास रियल नंबर्स हैं, मगर ये कितने यू अल्फाज है जहाँ पर ही नॉन ज़ीरो है वो सिर्फ इतने हैं. 1 2 यू कैन इन्यूमरेट देम. सो दिस लेमा इज वेरी पावरफुल. So let u alpha be an orthonormal set. It may be uncountable. Let u alpha be an orthonormal set. It's not basis here, it's just orthonormal set. It may be countable, it may be uncountable. Orthonormal set. If it is countable, then we have nothing to prove in that case. In an inner product space in an IPS, inner product space X, and X is an element in X, then with respect to this X, the following set, which we denote by EX. So for each X you can define this set EX. This set EX, it is a set of the members of this orthonormal set U alpha such that the inner product of this u alpha with x is not equal to 0, then this set and let this is the set, then this set ex is countable, then ex is countable set, then ex is a countable set, is a countable set, is a countable set. Okay, and countable it may be finite also, no? Countable set may be finite, finite sets are also countable, but in case it is countable infinite, it's a countable set like this u1 u2. so if अगर यही सेट जो आपने काउंटेबल लिया है अगर ये फाइनाइट होगा, फाइनाइट के केस में आपको कुछ नहीं देखना, इफ इट इज काउंटेबल इनफाइनाइट, इफ ex is denumerable, okay, countable infinite, if ex is denumerable, then you can talk about the convergence of series, because if it is finite then obviously the series will be the finite sum, then in that case the sum will automatically in our space x, okay, तो उस केस में आपको कुछ नहीं करना है, but in case the set is denumerable, then you can find out the limit, then what's this limit, inner product x u n, okay, n runs from 1 to infinity. अगर सेट फाइनाइट होगा उस केस में आप ये लिमिट आपको कैलकुलेट नहीं करना है, बट इफ द सेट्स countably infinite, so that means set is an infinite set, then you can find out this limit, and this limit you will see that this limit is equal to 0. उस केस में ये लिमिट किसके बराबर होगा, 0 के बराबर होगा. और if this x is Hilbert space, अगर ये x अब ये inner product space में ये चीजें होगी, अगर x Hilbert space होगा उस केस में सीरीज कहाँ कन्वर्ज करेगी, if x is Hilbert, if x is Hilbert space, okay, then we have this series x u n n runs from 1 to infinity, converges in x, okay, this series converges in x. to some y, किसी पॉइंट पर कन्वर्ज होगा, to some point y, to some y, such that the difference x minus y, तो ये जो एक्चुअली ये जो पॉइंट है ना ये x को भी कन्वर्ज कर रहा है. अगर आप पहली जो रिजल्ट्स आपने देखे ना, दिस सीरीज कन्वर्जेस टू x, बट इफ इट कन्वर्जेस टू सम अदर पॉइंट से y, then the difference x minus y, it will be orthogonal to each u alpha for all alpha. Okay, this is the fact. So given orthonormal set, the set ex, for any x in x, the set ex is countable. If it is countable infinite, then this limit is equal to 0, and in that case, if x is Hilbert space, the series converges in x. Suppose it converges to some point y, then the difference x minus y will be orthogonal to u alpha for each alpha. So first case, if this जो आपने x choose किया, if it is 0, then clearly the set u alpha such that inner product x with u alpha is not equal to, ये set क्या होगा, x the inner वो u alpha जहां पर इस 0 का inner product u alpha के साथ नॉन जीरो होगा, क्या होगा ये सर इस केस में, is काउंटेबल नहीं होगा. काउंटेबल तो आपको प्रूव करना है, काउंटेबल तो आपको दिखाना है काउंटेबल है, बट इस केस में पर्टिकुलर इस केस में क्या होगा, if x is 0, What's the inner product of x with u alpha?
0.
0. So it can never be not equal to 0. It can never be non-zero. So that
Yes.
means for the u alphas where this inner product is not equal to 0 is the empty set. We don't have any u alphas such that x u alpha is not equal to 0. So clear, therefore, and hence a finite set, and hence a finite set. तो इस केस में तो ये फाइनाइट सेट आ ही जाएगा. सो दैट्स काउंटेबल. काउंटेबल आपको प्रूव करना ये सेट, तो उस केस में काउंटेबल आ गया ये. सो वी अज्यूम दैट x इज नॉट इक्वल टू 0. सो we assume that x is not equal to 0. So let's see this for j varies from 1 to infinity. Let's define the set ej, e sub j, those u alphas. It's again the set of u alphas जैसे आपने x को डिफाइन किया, but here the condition is norm of x is less or equal to j times, it is a positive integer, a mod of the inner product x with u alpha. Okay, so let's this now let's fix g. Let's fix now g. कोई fix of g, say j equal to 1, 2, 3, any j you can fix. And suppose for any fixed j, ej contains say m elements. Suppose ej contains say these elements, these u alpha 1 m, say, okay, u alpha 2, u alpha m. Then so they are all in where? They are all in eg. Then norm x is less or equal to j times so it's j times mod of the inner product x with u alpha I. Let's write here alpha I. G is already there. Alpha I, okay, u alpha I for all I runs from 1 to m. Is it okay? क्योंकि u alpha 1 भी eg में है, इसका मतलब कि norm of x less or equal to j times mod of x inner product of x with u alpha 1. u alpha 2 भी ej में है, तो उसके लिए भी ये इनइक्वालिटी होगी. u alpha 2, u alpha 3, u alpha m, तो इनके लिए सब के लिए इनइक्वालिटी आपके पास आ जाएगी. So name it 1. Now let's see this. Now clearly this 0 is less than m times m is a positive integer. Norm x is also positive, okay. It's norm x square, okay, norm x square. Norm x is because x is not equal to 0, so both are positive, and this is equal to norm x square plus norm x square. How many times? M times. Now let's look at this, the last line. Norm x is less or equal to j times x u alpha 1. Each norm x for I runs from 1 to m. So first you put norm x is less or equal to j times inner product x u alpha 1. The next second norm x will be less or equal to j times inner product of mod of this x u alpha 2. फिर इसी तरह से जो थर्ड नॉर्म x है वहाँ पर आप लेस आर इक्वल टू j टाइम्स मॉड ऑफ द इनर प्रोडक्ट x u अल्फा 3. इसी तरह से mth नॉर्म x जो है वहाँ पर आप सब्स्टिट्यूट ये करोगे नॉर्म x लेस आर इक्वल टू दिस. सो एवरीथिंग इज लेस आर इक्वल टू, ओके, everything is less or equal to. So this is first, this is less or equal to, it will be now j square, okay, j square mod of inner product x with u alpha 1 square plus similar we have second one now j square mod of inner product x u alpha 2 square plus the jth one, mth one, j square mod of inner product x with u alpha m square by 1. By 1, and that's equal to j square times summation j runs from 1 to m inner product, j is the common factor, so it's here x, so let's not write here j, let's write here I. Okay, I runs from 1 to m x u alpha I square. Now from the Bessel's inequality, this is less or equal to, okay, so this thing is less or equal to j square times norm x square times norm x square. Okay, so this means norm x is not equal to 0. It means that m is less or equal to j square. So the number of elements in EJ, आपने assume किया था कि EJ में m elements है and that m is less or equal to j square. So that means number of elements in EJ is less or equal to j square. J square is a finite thing. So that means EJ has at most j square elements. So which means that therefore EJ contains at most j elements, j square elements. Okay, j square elements. So now next we verify that. So EJ is a finite set. Okay, next we verify that our EX is union of these EGs. Actually its j runs from 1 to infinity EG. Each EG is finite, so each EG is countable. So that means EX is actually the union of countable sets, which is a countable. So which means EX is countable. So सिर्फ आपको ये verify करना है. So ये हम कैसे verify करेंगे? Let's choose find any element here. So what's E alpha? E alpha is the set of U alphas. Okay. So EJ is also set of U alphas. Let's choose any U alpha. So let this U alpha, it belongs to EX. So then by definition, inner product of x with U alpha is not equal to 0. Okay. Fine. Also, so this means mod of the inner product of x with U alpha is not equal to 0. So this is a non-zero real number. Also we have also this U alpha is not equal to 0. Okay, also norm x is not equal to 0. So that means we have two non-zero numbers. One is norm x and second is this one, mod of inner product x with U alpha. So by Archimedean property I can find, so we can choose a positive integer, j such that norm x is less or equal to j times mod of inner product x with U alpha. Okay, but this is the condition for the elements of UJ actually. So this means U alpha belongs to some EG. Okay, U alpha belongs to EG. So that means any element, any member of UX is in some UG. So which means that U alpha belongs to union EJ, j runs from 1 to infinity. So thus this EX, it's subset of union EJ, j runs from 1 to infinity. So which means EX is, because because this is a countable set. Okay, actually it is precisely equal to this, but we need only one side inclusion because we want to prove that EX is countable. Now this set is countable, because each ej is a finite set containing at most j square elements. So each, that means each ej is countable. So this is the countable union of countable sets, which means that ex is countable. तो ये आपके लिए एक्सरसाइज होगी या so verify that this union ej runs from 1 to infinity is contained in ex. Okay, so therefore ex is equal to union ej, j runs from 1 to infinity, and hence ex is a countable set, and hence this ex, this is a countable set, is a countable set, this is a countable set. तो इसका जो रिमेनिंग पोर्शन है वो आपके लिए असाइनमेंट है. सो दिस इज, दैट्स वेरी सिंपल है. सो अगर एक्स सिल्वर स्पेस होगा उस केस में ये कन्वर्जेंस आपके पास आ जाएगी. इट विल कन्वर्ज इन एक्स, से इट विल कन्वर्ज एट पॉइंट वाई सपोज. सो देन यू विल सी दैट दिस वाई, it's a summation, it's summation inner product x with un, and that's same as x. So you can find the difference. That's very simple. This x minus y will be orthogonal to u alpha. So because what's this y u alpha will be equal to x u alpha. So you will see that actually this, suppose it converges to y, then you verify this. Suppose you assume that say this series it converges to y. Suppose this is y, x inner product x un, suppose this is equal to y, see the point is y, then you will see the inner product y u alpha, you will see this is equal to, so what's y is this sum. That's very simple. Now it's x un with u alpha, okay. So ये जो है स्केलर्स ये बाहर आ जाएगी सम से. इसमें सिर्फ अल्फा जो टर्म है ना वो रहेगी u alpha, रेस्ट आर इक्वल टू 0 because it is an orthonormal set. So it's equal to, it's same as x u alpha. You can see this is x u alpha, x u alpha के बराबर आ जाएगा. x u alpha भी यही आ जाएगा. अब ये है कि अगर इसमें इस सम में अगर u अल्फा नहीं है किसी जगह, सो उस केस में ये ज़ीरो है, उस केस में ये भी ज़ीरो है. और अगर इस सम में किसी जगह u अल्फा अपीयर हो रहा है तो वो जो u अल्फा होगा, सो इसमें सपोज x u अल्फा आ जाएगा, x u अल्फा स्केलर है, ये बाहर आ जाएगा. इनर प्रोडक्ट u अल्फा वो 1 आ जाएगा. और बाकी जो भी यूज है उनका इनर प्रोडक्ट u अल्फा के साथ 0 आ जाएगा बिकॉज द सेट u अल्फा इज एन ऑर्थोनॉर्मल सेट. तो उस केस में x u अल्फा आ जाएगा. ठीक है, तो दो पॉसिबिलिटीज है. या तो ये जो सम है अगर इस सम में क्या नहीं है, अगर इस सम में u अल्फा किसी जगह नहीं है, अपीयर इसमें नहीं हो रहा u अल्फा, उस केस में दोनों 0 के बराबर है. सो x u अल्फा इज सेम एज y u अल्फा फॉर ऑल अल्फा. ओके, फॉर ऑल अल्फा. So then from this you conclude that inner product of x minus y with u alpha is equal to 0 for all alpha. सिर्फ वो कन्वर्जेंस आपको बतानी है, तो वो एक्चुअली हमने एक जगह की है, उसका आपको यूज़ करना है बाय रीज फिशर थ्योरम. ओके, so that's the end of this lecture.